is equal to the open interval 4 minus 1, 4 plus 1, which will give us an open interval of 3, 5, which is also a subset of E. Then we can say that x is equal to 4 is an interior point. For our second example, let E be a subset of real numbers defined by E is equal to the interval open to 0 and close to 3, union with the interval open to 5 to positive infinity. If x is equal to 2 and c is equal to 1/2, the open interval x minus c x plus c is equal to 2 minus 1/2 plus 2 and 2 plus 1/2, which is equal to the open interval 1.5 and 2.5, which is a subset of E. Then x is equal to 2 is an interior point. We are now going to define the second term, the boundary point. A point x, element of E, is a boundary point if for all c greater than 0, the set of interval x minus c x plus c intersection with E and the interval x minus c and x plus c intersection with the complement of E are both non-empty. Now, in order for us to understand thoroughly what boundary point is, we have here our example number 1. Let E be a subset of real numbers defined by an interval E is equal to the interval open to 1 close to 5 union with the interval open to 8 to positive infinity. Let x is equal to 5 and c is equal to 2. First, we have to show that the interval x minus c and x plus c intersection E is non-empty. Here we have x minus c, or the interval of x minus c and x plus c intersection with E is equal to, as we have our substitution, the open interval 5 minus 2 and 5 plus 2 intersection with E, which will give us the interval open to 3 and close to 5, which means that x, or the interval of x minus c and x plus c intersection E, is non-empty. Secondly, we have to show that the open interval x minus c and x plus c intersection with the complement of E. Here we have the open interval x minus c and x plus c intersection with the complement of E is equal to the open interval 5 minus 2 and 5 plus 2 intersection with the complement of E, which is equal to the open interval 3, 7 intersection with the complement of E, which will give us the interval 5, 7, or open interval 5, 7, which means that the open interval x minus c and x plus c intersection with the complement of E is also non-empty. We have here our second example for boundary point. Let E be a subset of real numbers defined by an interval E is equal to open to negative 3 and close to 1, union with the open interval 6 to positive infinity. Let x is equal to 6 and c is equal to 1/2. First, we have to show that the open interval x minus c and x plus c intersection E is non-empty. Here we have the open interval x minus c and x plus c intersection with E is equal to 6 minus 1/2 and 6 plus 1/2 intersection with E, which is equal to 6 and 6.5. Close, which means that the open interval x minus c and x plus c intersection with E is non-empty. Secondly, we have to show that the open interval x minus c and x plus c intersection with the complement of E. Here we have the open interval x minus c and x plus c intersection with the complement of E is equal to 6 minus 1/2 and 6 plus 1/2 intersection with the complement of E, which is equal to the open interval of 5.5 and 6.5 intersection with the complement of E, which is equal to the interval open to 5.5 and close to 6, which means that x minus c and x plus c intersection with the complement of E is non-empty. Therefore, x is our boundary point. We are now down to the third term, the open cover. A collection of open sets of a topological space whose union contains a given subset is called an open cover. To understand this further, we have our first example for open cover. Given the set close to 0, 1, we can have the following open covers for the set as follows. The open cover or the open interval negative 1 to 2, the open interval negative 1/2 to 1/2, the open interval 1/2 to 2, and the open interval 1/4 to 3/4. These are open covers because the union of these open sets will contain the subset of our closed interval 0 to 1. Now for our second example under open cover, given the set closed interval negative 1 to 3, we can have the following open covers for the set as follows. Open interval negative 5 to 7, negative 2 up to 2 to 7, and 1 up to 2.5. These are open covers because the union of these open sets will contain the subset interval negative 1 and 3 closed. For the last term that we are going to define in this report, we have the compact set. A topological space X tau is compact if every open cover of X has a finite subcover. In order for us to understand further about the compact set, let me give you one example, our first example. Given that our set is equal to the set of 1, 2, and 3, and we have a tau which is equal to the set of empty set, X itself, the subset of 1, subset of 2, subset 3, subset 1, 2, subset 1, 3, and subset 2, 3. Let an open cover C is equal to the elements having subsets from tau. So we get subset of 1, subset 3, 2, subset 1, 3, subset 1, 2. These are the elements in our C as our open cover. The union of the elements in the open cover C is denoted by the union of C, which is equal to 1, 2, 3, or the elements 1, 2, and 3, which is equal to X, or the given set. Taking a subset from the open cover, so we have our open covers, we have 4 elements of different subsets. We say a subset from the open cover C sub 1 is equal to the set of the elements which are also subsets, the 1, 3, and 2. The union of the elements of the subcover C sub 1 is equal to the set of 1, 2, and 3, which still equal to the given set. Therefore, X is a compact set. Our example number 2 is similar to our first example. So suppose we have X is equal to the set of 1, 2, 3, and 4, and tau is equal to the set of empty set, X itself, the set 1, set 2, set 3, set 4, set with elements 1, 2, set with elements 1, 3, sets with element 1, 4, set with element 2, 3, set with element 2, 4, set with element 3, 4, set elements with elements 1, 2, and 3, set with elements 1, 2, and 4, set with elements 2, 3, 4, and set with elements 1, 3, 4. These all sets are the elements of our tau. Let an open cover C is equal to the set of the elements which are also subset. We have set 1 with element 1, set with elements 2, 3, set with elements 3, 4, sets with elements 2, 3, and 4. The union of the elements in the open cover C is denoted by union C, which is equal to the set with elements 1, 2, 3, and 4, which is equal to the given set X. Taking a subset from the open cover, say C sub 1. So our C sub 1 is a subset, is just a subset from our open cover C. We get the elements, the set with element 1 and the set with elements 2, 3, and 4. The union of the elements of the subcover C sub 1 is equal to the set of 1, 2, 3, and 4, which is still equal to the given set X. Therefore, X is a compact set. Aside from the 4 terms that we defined, part of this report is to state the theorem below and give 2 examples to illustrate the meaning of this. So, this is the theorem. A subset of R is closed if and only if it contains all its cluster points. Since the theorem is a biconditional statement, I am going to present 2 parts to prove the theorem. We will be proving the theorem by contradiction. Let's have first the first part. A is a subset of X is closed. This implies that the complement of A is open. If the complement of A is open, it implies that for all X element of A complement, there exists U sub X such that for all Y element of U sub X implies that Y is element of A complement. Suppose X is an accumulation of A that is not in A. For all U element of U sub X, there exists Y not equal to X with Y element of U intersection with A. Y element of U intersection with A implies that Y is not an element of A complement, which is a contradiction. A is a subset of X, contains all of its accumulation points, implies that A is closed. For the second part of our proof, also by contradiction, suppose A is a subset of X, contains all of its accumulation points. Suppose that the complement of A is not open. There exists an X element of A complement such that for all U element of U sub X, there exists Y element of U that is also in A. X is an accumulation point, which contradicts the premises. And that is the end of our proof for the theorem. Here are the examples for the theorem that we have just proven. The interval close to -1 to 1. It is closed because it contains all its cluster points. And for our example 2, the interval close to -1 open to 0, union with the interval open to 0 and close to 1. Still, it is a closed interval because it contains all its cluster points. And that is the end of my report. Thank you and God bless.